Hello there, welcome to this video where we're going to take a look at a problem in mathematics from a sixth term examination paper, or a STEP paper. So those of you who are doing A-level maths here in the UK, or further maths, and you're looking to go to university to do mathematics, particularly if you're applying to a higher rank university, it may be the case that you're required to sit a sixth term examination paper and achieve a particular grade as part of your entrance requirements to that particular university. So what we're going to do in this video is we're going to take a look at a problem from one of the past papers, the past sixth term examination papers, and we're going to take a closer look at the problem solving process. So it's not the specific problem that we're interested in or the specific solution to that problem, it's really how did that solution come about. So in this video, the idea is that I present my solution to this problem. And it is my solution. It's not the solution that I've taken from any mark scheme. It's my solution, which may or may not agree with the mark scheme. I don't even know if there is a mark scheme for the paper that I'm going to be working from. So it's my solution. And what I'm interested in is really trying to articulate how my solution kind of developed from start to finish. Okay. Because problem solving in mathematics involves a lot of, there's various difficulties that you encounter. You have to develop certain mental strategies. You've got to be able to change your perspective. Things like this, how you view the problem, generating ideas. This is all part of the problem solving process. And it's these kinds of things that I want to articulate. So this video is not meant to be part of any course, systematic course where I tell you how to develop your problem solving skills. All I'm trying to do is to give some ideas about things that you might try out, some things that might work for you. Some things that work for me won't necessarily work for you and vice versa, but it's essential nevertheless that you develop your problem solving skills in mathematics when it comes to if you're wanting to go on to do undergraduate mathematics. You need to develop your problem solving skills, and especially when it comes to doing a STEP paper or the MAT if you're required to do the MAT as well. Problem solving is quite a nebulous kind of thing. It's not something that can be necessarily taught in a direct way, and the whole point of these videos is that I try to just give you some ideas, try to stimulate some ideas that might help you along the way to developing your problem solving skills. What I can't do is tell you exactly what you need to do, unfortunately. That's up to you. How exactly you develop your problem solving skills, it's going to be down to the individual. All I can do is to try to give you some ideas. Okay, so the sixth term examination paper that we're going to be looking at is the Step 2 paper from 1990. So we're going back 35 years. And it's question 2 from this paper. Now, okay, I understand that because we're going so far back, the syllabus, the specifications will have changed over the last 35 or so years. But as individuals who are interested in mathematics, to have a high level of interest in mathematics, want to learn about mathematics, want to develop our knowledge and understanding of mathematics, and want to develop our problem solving skills, the fact that there might be some things on there that are that were on the specification then but are not necessarily on the specification now for, say, A-level maths or A-level further maths, that shouldn't be a problem. Okay. To develop your problem solving skills may involve you from time to time having to learn something that's, inverted commas, non-specification material. Okay, but that shouldn't put you off. You're not wasting your time when you do this. I did a lot of this particularly when I was doing my A-level maths and A-level further maths back in the day. Too long ago now for me to mention how long ago, but I spent a lot of time learning what was, for me at the time, non-specification material. And it really deepened my understanding of mathematics to the point where when it came to my A-level maths exams, for A-level maths and further maths exams, I didn't really have too much difficulty with the exams. Okay, so let's have a look at question number 2 then, from the Step 2 paper from 1990. So I've chosen this problem because I had some difficulties with this problem, and there's the 2 difficulties in particular that I had. So I'll explain what those difficulties were as and when. But throughout this video, it's not meant to be a model solution. I'm not intending to just present a model solution to this problem. I'm intending to kind of articulate the problem-solving process in all its messiness. Okay, so that includes ideas that I tried that didn't quite work or that totally failed. But nevertheless, I tried those ideas for various reasons, and I want to kind of demonstrate to you that this is a normal part of the problem-solving process. I don't want you to get the idea that the problem-solving is just a nice, straightforward thing, that a solution to a problem should just flow out of you, and you should just get the solution first time, every time, and it's perfect and everything, and there's no problems. That's just not the case, okay? So, what have we got to do here? So we're given some information. Prove that if A plus B plus C plus D is equal to pi, hopefully you're comfortable with radians, then sine A plus B times sine, let me get this right, A plus D minus sine B sine D is equal to sine A sine C. Okay, so in other words, we need to prove a trigonometric identity. By the way, I'll leave a link in the description to this video to so you can download this paper yourself, because I'm not going to write all of the question up on the board, so you can see it for yourself. I'll leave a link in the description. Okay, so with trigonometric identities, there's a million different things, a million different directions that you can possibly go in. Okay. By the way, if it appears that I'm looking below the camera, that's because I am. The question is here on my computer screen. And there's no systematic way of going about proving trigonometric identities, and this is something that people ask me all the time in lessons. Or they come to me and they say, "Oh, I'm having difficulty proving trigonometric identities," and there's always a look of disappointment on their face when I have to say to them, you just have to know your basic trigonometric identities, and you have to get practice at using them in various combinations. Okay, you will learn through experience what kind of things are worth looking for. But even then, no matter how much practice you get, there's always going to be some trigonometric identities that come up every now and again where you've really got to think in original and creative sorts of ways. Okay, so you've just got to be prepared to try things out, and that's all I could do here. So I was first introduced to trigonometric identities over 20 years ago. Don't like to admit that, but that's how it is. And even now, I've still got to just try things out. I've got to experiment. I've got to know my basic trigonometric identities, and I've got to have a certain level of confidence at using them, but I've also got to have a certain level of confidence at just experimenting with them, using them in various combinations. So sometimes you might try things out and they just don't work, and you look back and you think, well, that was really naive. But if it's the only idea that you had at the time, then just go for it. Okay, so after a few seconds of thinking about this, the first thing that I decided to do was to effectively use the compound angle identities, or the addition formulae, whatever you want to call them, on sine A plus B and sine A plus D. So you get something like sine A cos B plus cos A sine B times sine A cos D plus cos A sine D. And also, by the way, what I did, I didn't fully appreciate this at the time when I first set out to solve this problem. I thought it was kind of unusual that this minus sine B sine D was here rather than being over this side of the equality of the equals sign. So rather than it being sine A plus B times sine A plus D equals sine A sine C plus sine B sine D, for example, it would be effectively the same identity that I'd be trying to prove. There is kind of a reason why this is here. It's not essential. I automatically, in my mind, kind of put it over here, although I had a feeling that it was there for a reason. So sometimes bear that in mind. If something looks a little bit unusual, if it looks a little bit out of place, it might be there for a reason. It might be an essential reason. It might not be an essential reason. It turns out in this case, it's here. It doesn't have to be here, but actually it would make something a little bit easier further down the line, potentially. Depends how you go about trying to prove this identity. So what I'm going to focus on really is just this bit here. Okay, so if I just focus on the sine A plus B times sine A plus D, and forget about this bit for the time being, then I've just got this. Now, I can see that really the only thing for me to do here really is to just expand these brackets out, and I'm going to get quite a... What am I going to get? I'm going to get something like sine squared A cos B cos D plus sine A cos B times cos A times sine D plus and so on. Okay, and yes, I did do this initially. This was only because at the time I didn't really have any other ideas. So sometimes you just gotta, before other ideas start to come to you, sometimes you've just got to work with the idea that you've got, even though you know it's probably there's only a bit of an outside chance that it's going to work. Just keep going, because it might actually provoke something in your mind at some point where you see something, you think, actually maybe I could try this instead. So it is worth doing this. It's, as I've said, problem solving is messy. Okay, there's no guarantees, and you've got to find your own strategies, your own way of dealing with certain situations. Unfortunately, I can't give you any absolutes. I can't say do this, do that, do the other, and you'll get your solution. It doesn't work like that. You've just got to learn to deal with the various difficulties that arise. And sometimes in particular situations, even if you're a really good problem solver, you may be presented with a problem where you just don't see what you need to do. Unlucky. Okay, so yes, I went through this. I did a little bit messing around with this, and I was using... I've got my notes here, by the way, that I'm just referring to. So I tried using some, it looks like some double angle formulae, because you've got the sine squared A here, you're going to get a cos squared A. So I was thinking maybe I could make something work there, but it was just getting out of hand. Okay, so this was my initial idea, and it just wasn't working. But then there are some other identities, some trigonometric identities that are not used very often now in A-level maths, but they're really, really useful. Okay, so one of the identities, I'm going to have to try to remember it now, it's cos, so if we've got something like cos x plus y plus cos x minus y, for example, this is equal to, what do we get? Cos x cos y minus sine x sine y plus cos x cos y plus sine x sine y, which is just twice cos x cos y, for instance. So this is an identity. So forget about this. This is an identity. Okay, cos x plus y plus cos x minus y is identically equal to twice cos x cos y. We also have that cos x plus y minus cos x minus y is identically equal to, using a similar kind of approach, similar kind of argument, we get minus 2 sine x sine y. Okay, notice that there's a minus sign here. And these identities kind of popped into my mind, and I thought maybe I could make something work with these. So these identities, like I say, don't come up very often now with A-level maths, but that's not something that we should be bothered about, really. If it means for us to more effectively solve problems, means that we've got to learn an extra couple of trigonometric identities, so be it. Or at least become aware of them. At least become aware of those trigonometric identities, and maybe have an idea about how they're proved. So rather than trying to just commit them to memory, which I hate doing, by the way, with trigonometric identities, I hate learning umpteen different trigonometric identities. What I'd prefer to do is to learn an essential few and then figure out the rest for myself. Now, it does happen that because some of them I've used so much, even without really making a conscious effort to do so, I've kind of committed them to memory. Okay, so some of the identities that I was using here, for example, they're just in my memory banks, ready to use. But this identity itself was not. Okay, this is something that I've just had to kind of figure out in my head as I've gone along, and that's fine. Okay, all of this stuff, it helps you to better solve problems in future. So in particular, I'm going to be using this identity. Okay, so we're not interested in this one. There's also identities corresponding to sine x plus y plus sine x minus y, and so on and so forth. But it's this one that I'm going to be interested in. So let's have a look at how this might be used. Okay, because if you notice, we've got something that we could call x, and something here that we could call y. So in other words, this, and again, I'm just sticking with this. Forget about this for now. I'm just sticking with this bit. This is going to be identically equal to cosine of x plus y, which is going to be a plus b plus a plus d, minus the cosine of x minus y. So a plus b plus a, x minus y minus a minus d. Okay, let's get it right. Okay, why is this useful? Well, at first I couldn't really see how it was going to be useful. It was just another idea that I had, and I thought I'm going to try it out and see where it goes. So what we end up with is that this is identically equal to the cosine of, now I want to get this right, so I took some certain steps when I did this. 2a plus b plus d minus cosine of b minus d. Okay, time for a sip of coffee. Oh, no, this isn't quite right. For those of you with sharp eyes will realise that I forgot to divide through by minus 2 with the identity. Remember, it was cos x plus y minus cos x minus y is equal to minus 2 sine whatever. So actually this should be a half, minus a half plus a half that, and minus a half plus a half. Oh, I'm glad I saw that. Oh, that would have been a disaster. Okay, so the next thing I did was realize that up here, this 2a plus b plus d, we need to use this somehow. Okay, if you've been given a bit of information, it's always important that you make sure that you include that bit of information. So if it's a well-formulated problem, which it typically will be, if it's on an exam, if it's on a mathematics exam, then seldom will you be given information that is superfluous. Okay, so if you're struggling to solve a problem and there's a bit of information that you haven't used, and you wouldn't believe how often this happens, then that's probably the reason why you're struggling to solve the problem. It could be one of the reasons. I'm not saying that there's any guarantee that once you realize that the solution will automatically just click into place. You've still got to figure out how that bit of information is going to be incorporated into a suitable solution. But it's going to be very difficult, if not impossible, for you to find a solution if you don't even try to use that bit of information. Okay, and it's as I said, it's surprisingly common with GCSE and A-level math students trying to solve problems, and they'll say, "I've got stuck. I can't make any progress with this," and they've ignored a bit of information because they didn't understand it, or they just didn't know what to do with it. So what they do is they just kind of brush it to one side and then wonder why they can't solve the problem. Well, that's probably one of the reasons why you're not getting anywhere. Okay, right, so let's get back on track with this. Right, so using this bit of information, I can see then that 2a plus b plus d is going to be equal to what? Pi plus a minus c. Okay, so just add a to both sides of this and then subtract c from both sides. So in other words, this I can replace with this. So I get minus a half cosine of pi plus a minus c plus a half cosine b minus d. Okay, so far so good. And then I can use another trigonometric identity. In fact, I've already used it. I'm going to kind of group this as pi plus a minus c. And I'm going to, inverted commas, expand this out. Now remember, I'm sure you know this, but cos a plus b is not equal to cos a plus cos b in general. Okay, why is that? Because cos is not a number, cos is a function. Okay, this is not cos times a plus b. Now I'm sure that most of you, if not all of you watching this, are perfectly aware of this, but I really want to emphasize this. Don't be lazy when using your trigonometric identities. If you want to think about what I'm about to do as expanding out cos a plus b, then do so, but it's not how you would expand out brackets if you had a number here or something like that. Okay, I'm sure that you're fully aware of it, but just to emphasize the point. Okay, so we've got cosine of pi, cosine a minus c. We've got the minus half there, so it's going to be plus a half cosine, sorry, not cosine, sine pi, sine a minus c, plus a half cosine b minus d. Perfect. Right, so sine pi equal to 0. Bye-bye. So what I'm left with is half cosine b minus d minus a half, cos pi, cosine of pi is minus 1. So it's going to be plus a half cos a minus c. Okay, so it's at this point where this here could be quite useful. Okay, now I just carried on with this. Remember, I was focusing just on this bit here. So I just carried on doing what I was doing here. But in retrospect, once I went back and kind of reviewed my solution, I realized that something that I'd done here at the next step could have not necessarily been totally avoided, but could have been facilitated a little bit. Or if I paid more attention to this, it might have given me a bit more of a clue, a bit more quickly as to what to do. But anyway, I eventually got there. Eventually got to what I needed to do, and what I did was, okay, so I expanded this out again, understanding that in the right sense. So I take the half out as a common factor, and I get cos b cos d plus sine b sine d plus cos a cos c plus sine a sine c. Okay. Right. So then what did I do? I need to refer to my notes. Right. So then I kind of isolated this and this, because notice now that I've got the sine A sine C that I need, and I've also, because I was thinking about this over here, I'm thinking I really want to keep these in here, right? And this is a good thing to do, to pay attention, to have in mind something that you're aiming for, okay? So the thing that you're aiming for might not necessarily always be the right thing, by the way, but at least if you've got something to aim for, you've got a direction to go in. Which is better than no direction, because sometimes people, when they're trying to solve a problem, they just don't have any idea about where they really need to be going, and they're just trying to go all over the place at the same time. They're literally being pulled in a million different directions, but they're doing it to themselves. So it's better to have a much more kind of definite idea about where you want to go. There's no guarantee that it's going to be right. It might end up being in the wrong direction. There's nothing you can do about it. Sometimes that will happen, and it's happened to me plenty of times, even in exams, unfortunately. Okay, so I want to keep these in here, but that means that I need to get rid of these things now then. The cos b, cos d, and the cos a, cos c. Okay, how am I going to get rid of these? So let's have a look what I can do to get rid of them. I can do the following. Notice also that, okay, if I were to expand this out, I'd only have half sine b, sine d, and sine a, sine c. So even though I want to keep these, I've still got kind of an additional problem, which I am aware of, that I've only got the half here. Okay, that we'll sort that out in a second. So what I'm going to do is I'm going to kind of isolate the cos b and the cos b, cos d, cos a, cos c, and figure out what I can do with that. So I get cos b, cos d, plus cos a, cos c. So we're doing a little aside calculation here. So it took me a little while to kind of latch onto this idea. Be prepared to do that. Be prepared to give yourself the time that you need. I know in an exam it's going to be difficult. I was sitting here at my desk without the time pressure of an exam. Okay, so it's easy for me to say, but believe me when I say I've been in that situation where I've been in an exam. I know the stress, I know the pressure that you feel, but you do still need to at least give yourself some time to try to think about things and be prepared to try things out. So what I did was I wrote this in a very particular way. I wrote cos b, cos d, plus cos a, cos c, plus sine b, sine d, plus sine a, sine c, minus sine b, sine d, minus sine a, sine c. So what have I done here? I've effectively added 0, but in a very, very particular way, okay? Because I've added the sine B sine D on, and then I'm subtracting it off. I've added the sine A sine C on, and then I'm subtracting it off. Why would I do that? It seems such a bizarre thing to do, because then I can group this with this, and I can group this with this. And what I end up with is cos B plus D plus cos A plus C plus sine B sine D plus sine A sine C. Okay? By the way, I'm not suggesting at all that this is the best way of going about solving this problem. This is just my solution. I'm sure that there will be a much more efficient way of going about this, but this is just how I did it. Okay? So let's... So then what I did was I recognized that B plus D is equal to pi minus A plus C. So bring that down here. I get cos pi minus A plus C plus cos A plus C plus all of this here. Well, it turns out that this, if I use trigonometric identities again, I'm going to get cos pi, cos A, so it's going to be cos pi, cos A plus C, plus sine pi, sine A plus C, plus cos A plus C, plus this sine B sine D, plus sine A sine C. But cos pi is minus 1. So that's just going to be minus cos A plus C. Sine pi sine A plus C is, sine pi is 0. So then I've got minus cos A plus C plus cos A plus C, cancel, cancel. What am I left with? Sine B sine D plus sine A sine C. In other words, cos B cos D plus cos A cos C, under this condition, is equal to sine B sine D plus sine A sine C. Okay, so what I end up with then is 2 sine B sine D plus 2 sine A sine C, all multiplied by half here on the outside, and I get the identity. Okay, because remember what I started with? What I started with was this. I've shown that this is identically equal to sine B sine D plus sine A sine C, which with a little bit of a rearrangement gives me the identity that I needed. Okay, so it's a bit of a faff. Okay, I'm sure that there will be a better way of going about it. It's just I haven't bothered to look. I was happy with this. I just couldn't really be bothered to have a look, see if there's a better way of going about it. Maybe one day I will. If you find a better way, please let me know. I'd love to hear what kind of tricks what kind of better approaches are out there. So I'm not saying in these videos with the solutions that I present, I'm never going to claim that the solutions that I present are the best solution, and that's not even the point. The point is that I'm just communicating my thought processes as I was solving the problem. Okay, so if you're looking for a quick model solution, you're in the wrong place. Okay, so then we move on to the next part. We've finished with that. Notice this identity only holds under this condition. A plus B plus C plus D is equal to pi. You've got to remember that. Okay, so if we get rid of this stuff. And this next part was, I had several difficulties with this. So let me read out what we need to do. The points P, Q, R, and S lie in that order on a circle of center O. Okay, so this is our circle of center O. we've got P, Q, R, and S. Okay, P, Q, R, and S. So naturally, PQRS is going to be a cyclic quadrilateral. Prove that PQ times, so let me get this right. PQ times RS plus PS times QR is equal to PR times QS. Okay. Right. So just so you know, this is Ptolemy's theorem. You don't need to know that necessarily, but this is a well-known result called Ptolemy's theorem. One of the difficulties that I had was I know how to prove Ptolemy's theorem without using trigonometry. Okay, because that's the context in which I've worked with this theorem before. So it's not some special superpower or something like that. It's just the proof of Ptolemy's theorem that I know does not involve trigonometry. So the first thing, we're not instructed here how to prove this. We're not given any indication about how to prove it. But my guess is that we somehow need to try to involve this. Now, I don't know whether if this came up on a step exam now or something like that, and you didn't use this, you still proved Ptolemy's theorem, but without using this, even though you proved this in the first part, I don't know if you would get your marks or if you'd lose your marks. Or if you've just been instructed to prove Ptolemy's theorem or prove this theorem, as long as you come up with a valid proof, as far as I'm concerned, you should get your marks, right? But that's kind of beside the point. I thought, my thinking was, if I'm going to prove this, rather than just proving it any old how, I want to try to find a proof that uses this. Okay, that uses this identity that we've... That's an identity, by the way. Actually, I'm going to... No, let's get rid of that. I don't like it. I want to prove Ptolemy's theorem using this, because that is, to me, the kind of mindset that I would expect an A-level mathematics student to be to have going into a step exam. Okay, to be having a tendency towards using ideas from trigonometry rather than ideas from pure geometry, or the kind of geometry that you might see in Euclid's Elements or Apollonius's Conics or something like that. Okay, there's nothing wrong with that. I like that type of geometry. I love that type of geometry. But it's just not. It's not something that's very well known at this stage, particularly at A level. Even going to high level maths, you typically won't learn about pure geometry. Okay, so that was the first problem that I had. I already know how to prove this in a certain way, but I've got to try to drag myself away from that idea and come up with something else. Okay, that was the first problem. The second problem was that I got fixated. I had an idea and I got too fixated on it. Okay, and this is always a danger. This is a pain in the ass when it happens, especially in an exam, when you can't seem to get a certain idea out of your head. It just happens sometimes. It's unfortunate. So I'll try to explain what my original idea was and kind of explain why it didn't seem to be working. Okay, so immediately I thought about this as a cyclic quadrilateral. But notice that in the problem, in in the information that we're given, we're told that P, Q, R, and S lie in that order on a circle of center O. Okay, so I thought, that they're mentioning the center here, and it would seem to me that they're mentioning the center for a reason. Okay, so I kind of got fixated on that. So I thought, right, what's a typical thing to do here? Well, one thing that you would have a tendency to do maybe is to draw radii out to each each of the points P, Q, R, and S. Okay, it's perfectly legitimate thing to do, and it's very useful in proving, for example, that the opposite angles in a cyclic quadrilateral add up to pi or 180 degrees, whatever you prefer. If I thought about that a bit more carefully, I might have clicked on a bit sooner to what I needed to do, by the way. But what I did then was thought, right, these are isosceles triangles. So if I just call that angle A, then this is going to be A. If I call that B, well, that's going to be B. If that's C, then that's going to be C. And if that's D, then that's going to be D. And here I've got the added bonus that A plus B plus C plus D are going to add up to pi, which is exactly satisfies this condition, because to use this identity, I'm going to have to make sure that that condition is satisfied. Remember what I said? This is not an identity unless this is satisfied. I think I said that. I think I mentioned it. If I didn't, then okay. So we seem to be onto something that could potentially work here, right? So then I thought, okay, I've got the lines PQ, QR, RS, PS, but I need the lines PR and QS drawn in. Okay, so let me draw those in. But then I recognize I've kind of got a problem here, in that what I wanted to do was kind of use the sine rule, I guess. But I've got a bit of a difficulty here, because it's not as simple as saying, oh, sine A plus B over PR is equal to sine A over QR plus sine B over PQ, for example. Which is, naively, this was kind of the direction that I was going in. Without really thinking too much about the detail, this was where my mind was taking me. Okay, why doesn't this work? Well, because unfortunately, this line that I've drawn from P to R, the triangle that's formed, PQR here, the angle here is not equal to A, or the relevant angle is not equal to A. It's equal to A minus a bit. Okay, so maybe I call that little bit X. And therefore, because OP and OR are radii, this is an isosceles triangle, so OPR is an isosceles triangle, and therefore that angle is also going to be X. So it's going to be more like sine A plus B over PR is equal to sine A minus X over QR, which is equal to sine B minus X over PQ. I thought, well, maybe that's not the end of the world, because okay, these are just kind of representatives of angles here. So the actual angles that I end up dealing with might not be A, B, C, and D. It might be A minus X, B minus X, but it might be C plus X and D plus X. It might be. In which case, great, the angles still add up to pi. And maybe I can make something work with all of this. So then I looked at drawing a line from, what was the other one, Q to S, doing a similar thing. Okay, so doing a similar kind of thing. Diagram's not drawn very well, but what you get is something like sine A plus D is equal to, over QS, is equal to, now it turns out it's not going to be C minus X and D minus X or something. It turns out to be something, let me have a look what so looking at my notes, and by the way, my notes are not necessarily reliable. You end up with something like A plus, not A plus Y, yeah, A plus Y over PS is equal to sine D plus Y over PQ or something. it's kind of beside the point anyway, because this idea doesn't go anywhere. So the point is that when I draw another line in here from Q to S, kind of difficult on here, it's the same kind of thing that happens. The angle here is it's not quite D, it's D plus or minus Y, it depends how the diagram's drawn, so it could be D plus Y or D minus Y. And similarly for A, it's not going to be A, it's going to be either A plus Y or A minus Y. And it doesn't work because there's no guarantee that the angles, notice by the way that C doesn't seem to be featuring here, that can be fixed because we can figure out that sine A plus D is equal to sine B plus C, for instance. So I can look at things from the other perspective here, and I can get that this is equal to sine. So if we've got D plus Y, maybe I'll change it to minus actually. A minus Y, D minus Y. And then we also get sine B plus Y over PS, I think. Is that right? Sorry, SR. Which is equal to sine C plus Y over QR. Again, I'm doing this very roughly because really this idea doesn't work out. So then the angles I seem to be working with are A minus X, B minus X, we've got A minus Y, D minus Y. However I combine these angles, A, B, C, and D, whether I've got X's involved, Y's involved, they don't seem to add up to, I can't seem to guarantee that they're going to add up to pi. Okay, so I can figure out the relationships that, for example, is it B, something like B minus Y equals D plus X, and A minus X is equal to C minus Y, for instance, and things like this. Again, these might not be quite right, but just to give an idea about the kinds of ideas that I was having. So I can try and express all of these angles with either plus or minus X, but unfortunately I can't get 2 plus X and 2 minus X to kind of balance out to make the pi. It just doesn't work, okay? And believe me when I say I tried to make this work, but I was missing something very, very, very obvious, okay? And this is how it happens sometimes, and you kick yourself when this happens, but it just happens sometimes. So let's kind of forget about this. It doesn't work, or I couldn't get it to work anyway. Part of the problem was how I was assigning the angles A and B, A, B, C, and D. Okay, that's part of the problem here. If I'd been a little bit more careful, P, Q, R, S, I would have possibly first of all realized that the center, I don't even need to worry about the center. I do need to connect the lines, the points P, R, and Q and S. I know that opposite angles of a cyclic quadrilateral add up to pi, but I can assign these angles in a much better way. So if this is angle A, for example, then this is also angle A. Why? Because they're the angles subtended at the circumference by the same arc, or chord, whichever you prefer. Ha! Right, this was the light bulb moment for me. So if that's angle C, that's angle C. If that's angle D, that's angle D. If that's angle B, that's angle B. Now this works. This is a much more convenient idea, because now I get sine A plus B over, where's A plus B? Over PR is equal to sine D over SR, which is equal to sine C over PS. And because sine A plus B is going to be equal to sine C plus D, we also get that these are equal to sine A over QR, which is equal to sine B over PQ. And similarly, sine A plus D over QS is equal to, we get a whole bunch of bunch of equalities here as well. So sine C over PS, which is equal to sine B over PQ. Similarly, sine A plus D is equal to sine B plus C. So we get sine D over SR, which is equal to sine A over QR. Okay. And then it's simply a case of choosing amongst these which are going to be useful to kind of combine, and in what way. So I get sine A plus B over PR times sine A plus D over QS is equal to, I'm going to refer to my notes here, so it's sine A over QR times, no, it's not, sine A over QS. I've made an error somewhere. A plus B sine A over QR sine B plus C sine A over. I've made an error somewhere. I can't see where. Let me look at my notes. Sine C over PS, sine D over SR, QR. No, sorry. Sine OQ. Something's not right here. Oh, no, sorry. I know what I've done. I'm not using these. I'm using this identity. So I'm replacing the sine A plus sine B times sine A plus D with sine A times sine C. I know what I've done. Over PR times QS plus sine B sine D over PR times QS. Okay, so I've just literally replaced, maybe I should write that, this expression here over PR times QS with sine A sine C plus sine B sine D. Okay, and then using what I've got here, I can write, for example, that sine A plus B over PR, sine A plus B, it's actually sine A that I need. Yeah, okay, so sine A, we'll get there in the end. Sine A is equal to QR times sine A plus B over PR, which in turn is equal to sine A plus D over QS times QR. Sine B is equal to PQ times sine A plus B over PR, which is equal to sine B PQ sine A plus D over QS, and so on and so forth. So you get expressions for sine C, sine D in a similar way. And then, so you replace the sine A here, for example, sine A sine C, you would replace with is equal to, and you've got to do it in the right way. So it's QR over QS times PS over PR sine A plus B times sine A plus D. Sine A plus B sine A plus D, for example. So you could replace the sine A sine C with this expression, replace the sine B sine D with a similar expression, and then it's just a rearrangement. So I'm not going to write all of the details out. Again, really, I just want to communicate the idea. But that's how you would you could prove this using this, which is a bit of a faff. The derivation of this was a bit of a faff, but this is a faff as well. But this is the kind of thing that you've got to do with step problems. Okay, so we'll consider this solved. Now, how might you go about proving Ptolemy's theorem without using trigonometry? Okay, well, I'll just give an idea of it. I'm not going to go through the proof of it. And it's certainly not a proof that I came up with, by the way. I'm not going to claim at all that I came up with this proof. So what you can do is, like, you can take one of the sides, say QR, and you can produce it as far as is necessary, and you draw a line from, say, S here to this line produced to a point P, such that this angle here is equal to B. Okay, and then what you can do is prove that the triangle QSP is similar to the triangle, where are we? It's similar to the triangle PSR. And also that the triangle SRP is similar to the triangle, which triangle now? Triangle SPQ. Okay, I'm not going to go through the details of this. Is it SPQ? Yeah, SPQ, pretty sure. And then once you've shown that these are similar, and it's really just an angle chase. You're just checking angles, really. And then because you know that this triangle is similar to this triangle, you can consider the ratios of the various sides, and the result eventually pops out. So I'm not going to go into the details of it, but this avoids all explicit reference to trigonometric functions or anything like that. Although trigonometric functions are effectively just ratios of lengths of sides of right-angled triangles, it kind of is indirectly involving trigonometry, just not in an explicit way. Okay, so if you've made it this far in the video, well done, because this has been a slog. Even with my notes here, this has been a challenging problem to get through. If there is anything that you want some clarification on with this video, which I imagine there's a lot of stuff, please leave a comment in the comment section. I don't expect that I've explained everything perfectly at all in this video. That's not the point. The point is to try to encourage some sort of dialogue and to stimulate some ideas in you to help you develop your problem solving skills. If there is anything that you want to ask, please leave a comment in the comment section. Hit the subscribe button. As of the time of making this video, I've only got a few subscribers, so it'd be really great if you could help me out and hit the subscribe button, hit the like button, and that brings us to the end of the solution to this problem and the end of this video. Thanks for watching.